Today I'm going to talk about aerospace computation, which is basically how we can use mathematics and simple physics to design future aircraft. So as we know, flying has become cheaper and safer now, so more and more of us fly or use aircraft. And like this rapid growth in air transportation actually comes with the undesirable environmental impact of aviation. For example, noise, local air quality, and climate change. So we have heard a lot about the environmental concerns about everything now, about energy, about aircraft, and we are going to talk about that later. So NASA in the US actually set out the goal to design the environmentally responsible aircraft, which is for the next generation aircraft, by reducing fuel burn by 50%, harmful emissions by 75%, and noise impact in the communities surrounding airports by 83%. So we know that the aircraft that we know now has the tube and wing configuration, and that's actually has been perfected to be very efficient and safe. So in order to design the next generation aircraft, we need to push the boundary even further by start considering unconventional configurations. So for example, as shown here at the top left is the flying wing, at the right is the blended wing body or BWB configuration, and then at the bottom we have the joint wing configuration. But we don't have any historical data or past experience corresponding to these designs. So what we can do is to use aerospace computation. So what is computational engineering? So in general, it is actually a tool to predict and optimize the performance and safety of complex systems before physical prototypes are built and tested. So for example, when we talk about aircraft, it's not easy to build the the full scale of aircraft, fly it, and to do the testing and experiments with the designs. It's because it's dangerous, it's very expensive, and we need a lot of time and money and space and even people to do it. So that's how the mathematical models can help in the analysis and optimization before the production. So in that way, we can also explore many designs, for example, to go beyond the conventional design to consider the unconventional configurations. So there are two main components in aerospace computation. First, we need to build the mathematical models to be able to simulate the aircraft operation. And next, we need to perform optimization. So what is an optimization? So it is basically a systematic method, computational method, that can help the designer to achieve the best possible results under given circumstances by varying some design variables. So I'll come back to optimization formulation again later. So, but in terms of aircraft design optimization, typically we only look at one flight condition in the optimization. So for example, we optimize the performance of the aircraft when the aircraft is actually flying in the air at certain angle, certain speed. But the limitation is that it's only optimized for that particular condition, and it can actually cause performance degradation at other conditions, which we want to avoid, because as we know, aircraft goes through different flight conditions during flights. For example, from takeoff, climb, cruise, descent, and landing. So the approach that I propose is to perform multi-point optimization, where instead of looking into one flight conditions, we actually consider multiple flight conditions and include them in the optimization. So we can use the weighted average objective functions as shown here, where we need to evaluate the objective function fj at different flight conditions or different points, and assigns the weights wj. But now the question becomes how to rationally select the points and derive the weights for the formulations. So what we want to have is to have the problem formulation, the multi-point formulation that actually reflects how the aircraft actually operates to be relevant to the real world situation. So back to the optimization problem, just to give a very brief introduction of the basic aerodynamic forces acting on the aircraft during operation, we have in a vertical direction lift and weight, and then in the horizontal direction we have thrust and drag. So basically, the bottom line is if we want to make sure that the aircraft can actually fly and move forward, we need to make sure that we have enough lift and thrust. So to model these forces, we need to model the airflow around the airfoil. So on the right-hand side is the airfoil is just a cross-section of the wing. So there are three main components in optimization problem. The first one is objective function, which is what we want to achieve. For example, we want to minimize drag, we want our structural weights, fuel burn, or direct operating costs. And then design variables refers to the variables that we can vary in the optimization. For example, the shape of the aircraft. And constraints are the conditions or restrictions that we want to impose on the designs. For example, we want to make sure that the aircraft actually satisfies the lift requirements, stall, structural failures, mission requirements, field lengths, etc. So back to the idea of formulating the problem in such a way that it reflects the operation of the aircraft. So what I developed is a detailed mission analysis procedure to evaluate the fuel burn as well as to know the flight conditions distribution of the aircraft during operation. So to do this, I modeled the mission profile and I divide into different segments, which are takeoff, climb, cruise, descent, and landing, as shown in the diagram. So I analyze each segment and then combine them together to have a valid and continuous mission profile. The problem with this analysis is that it is very computationally expensive because it requires a lot of, well, actually it could reach millions of performance evaluations of the aircraft. And since aircraft system is a very complex system, it can become very expensive. It might actually take days to finish an analysis. So the solution is to develop a surrogate-based mission analysis procedure. It is a purely mathematical computational solution where I use surrogate models or approximation models to approximate the aerodynamic force and moments coefficients required in the analysis. So we reduce the number of performance evaluations of the aircraft from millions to the number of samples required to build the surrogate models. So what are surrogate models? They are basically mathematical models to approximate a physics-based model that is simpler, cheaper, and much faster to evaluate. If we look at the black box models, we can rely only on samples, which make things simpler. So we don't really need to know the governing equation of the system. We just need to have samples with inputs and outputs values. However, this surrogate model might have limited capability to model highly nonlinear function profiles, which have different characteristics in different design space. So I developed this mixture of experts approach where the basic idea, which is basically developed to address the issue we have with conventional surrogate models. So the basic idea is to have multiple local models with different parameters. So for example, here I show the partition of an input space to different parts shown in colors. So this basically we use the divide and conquer strategy to build this model. So using surrogate models in the mission analysis is actually very accurate with less than 2% range estimation errors, and the speed up is quite significant, at least 70 times. So now we have an accurate and efficient method to generate flight condition distribution data based on some flight mission data that we can find in the publicly available database. So on the left-hand side, I show the distribution of the flight missions in the different payload and range value. This data actually refers to the actual Boeing 777-200ER US mission data in 2011. So I use this data to derive the multi-point aerostructural problem that I'm going to talk about next. So aerostructure, what is aerostructural? So basically, instead of looking at the aerodynamics discipline of aircraft and structural disciplines, I'll look at the combined coupled aerostructural discipline. So the reason is because we think aircraft as a rigid body, like the wing looks rigid, but actually when it's flying up in the air, the wing deflected, so there's an interaction between the structural change of the wing and the airflow around the cross section of the wing. So we need to take this interaction into consideration to be able to model the aircraft performance properly. So in this optimization, the design variables, or the variables that we can vary, include some global design variables which affect both aerodynamic and structures discipline, including some of the shape variables as shown on the left-hand side of the top view of the aircraft over there. And for aerodynamic design variables which affect the flow directly, I have angle of attack, or the angle of aircraft flying relative to the wind flow, and the tail angle for the stability. The structural design variables are basically the thicknesses of the structural components. Those are the right-hand side, top right, is the blow-up picture of the wing. So we have upper skin, lower skin, and all the strengthening parts in between. So the coupling between these two disciplines is taken care of by the force and displacement transfer approach. So the aerodynamic solver will analyze the forces acting on the structural of the aircraft, and then the structural analysis will look at the displacement, which then affects the aerodynamic flows around the aircraft. So for the objective function, or what I want to minimize, is the weighted average fuel burn, which I want to look into the fuel burn of all the flight missions of the Boeing 777 that I showed earlier. But instead of computing the fuel burn for each flight mission, I actually linearize the problem, so I can convert this multi-mission problem into multi-point for optimization problem. So it's much cheaper to analyze and much more efficient. For the constraints, I'll look at geometric, aerodynamic, and structural constraints. So in the last few slides, I just discussed the results briefly. So here I mentioned about the motivation of doing multi-point optimization compared to single point optimization, and here we can see the benefit of the multi-point optimization. So here I'm showing the drag divergence curves, basically the drag distribution at different flight conditions. And lower drags are always better. So the green lines correspond to the initial design, red lines correspond to the single point design, and blue lines correspond to the multi-point optimized designs. So we can see that the single points really result in localized performance gain. So the reduction in drag is only at a certain area, whereas with the multi-point optimization, we can obtain a more consistent performance gain, which is desirable. When we look at the fuel burn reduction, we go back to the flight mission distribution, and I compute the fuel consumption between the initial and optimized designs for both the single point and multi-point optimization cases. What I found is the single point optimization, some flight missions actually burn more fuel with the optimized design, which is undesirable. And the multi-point optimization actually consistently reduce fuel burn at all representative flight missions. And when we look at the aggregate fuel burn reduction, the single point only reduced by less than 2%, whereas the multi-point reduces by almost 7%. So in terms of monetary value, it is actually about billions of dollars, so we can actually save significant amount of money by doing so. So just to summarize and conclusion, I just briefly discuss how we can use mathematics and computing techniques to help design aircraft, and some strategy, for example, using surrogate models to reduce the computational cost to formulate the optimization problem in such a way such that the results are actually relevant to the actual flight operating envelope of the aircraft that we are talking about. So in the future research direction, a lot of people are asking, so what is there in the aircraft design? So basically we focus on the environmental consideration, environmental concerns, the limitation of the fuel. Fossil fuels are non-renewable, and alternative fuels, renewable energy have become hot topics in research now. So in that case, where we are actually going into a new uncharted area, the aerospace computation will play an even greater role, because we can rely on computation, mathematics, computation, simulation, optimization to actually explore the design and try different aircraft designs the future. So that's all for the technical content of my talk. And I was asked to talk about some personal mission in terms of research, science, and engineering. Okay, I'll go back to Indonesian now. Seperti yang saya bilang, saya sudah menghabiskan hampir setengah hidup saya di luar negeri. Tapi kalau misalnya soal visi ke depannya, secara pribadi saya ingin suatu saat kembali ke Indonesia karena saya beruntung untuk mendapatkan kesempatan sekolah di 3 negara yang berbeda, Singapura, Amerika Serikat, dan Kanada, dan sekarang kerja di Hong Kong. Jadi mendapat exposure to what science and engineering are like overseas, dan juga untuk berinteraksi dengan bermacam-macam orang Indonesia di luar negeri. Dan orang Indonesia itu potensinya sangat-sangat tidak kalah daripada orang-orang luar negeri. Jadi sebenarnya negara kita kaya sekali, brain powernya itu benar-benar ada. Jadi saya pribadi ingin kembali ke Indonesia suatu hari untuk berbagi benefits yang saya dapat dari luar negeri selama bersekolah, di-share dan dibagi kepada rekan-rekan di Indonesia yang mungkin tidak cukup beruntung untuk bisa ke luar negeri. Dan juga kalau soal pendidikan, saya percaya untuk science and engineering sebenarnya harus dipupuk mungkin sebelum tingkat universitas. Mungkin dari SMP, SMA sudah perlu dikenalkan seperti apa sih science, engineering, dan penelitian itu. Karena saya sampai sekarang masih berhubungan baik dengan guru-guru SMA saya, dan mereka bercerita kepada saya salah satu challenge yang mereka hadapi sebagai guru SMA adalah murid-murid tidak menyadari bagaimana mereka menggunakan ilmu yang dipelajari selama SMA. Di kemudian hari mereka tidak mendapat bayangan kalau misalnya ilmu-ilmu dasar itu bisa sebenarnya dipakai untuk menyelesaikan masalah-masalah di berbagai bidang, science, engineering, kedokteran, dan sebagainya. Dan kalau misalnya soal kepemimpinan di bidang penelitian, sepertinya saya bisa berbagi 3 hal: mentoring, networking, dan proaktif. Mentoring itu sangat perlu karena pengalaman saya ketika saya memulai program PhD di Kanada, the first question my advisor asked was, kamu mau jadi apa? Mau masuk academic or industry? Dan dari awal saya bilang saya mau menjadi akademisi, saya mau menjadi dosen, mau menjadi profesor suatu hari. Jadi cara dia membimbing saya berbeda dengan cara dia membimbing orang-orang yang ingin menjadi konsultan, ingin menjadi kerja sebagai engineer di perusahaan. Dan itu benar-benar dia terus mentor saya dalam arti begini loh kehidupan profesor, begini loh kehidupan dosen, kamu harus bisa begini, harus bisa begini. Dan sekarang saya menjadi dosen muda di Hong Kong, department head di department saya itu juga assign somebody to be my mentor. Jadinya dan saya benar-benar karena sebagai dosen muda yang beberapa bulan sebelumnya masih menjadi pelajar, itu tuh sangat-sangat susah dan a lot of things are different gitu. Jadi benar-benar ada mentor yang selalu membimbing saya. Kalau misalnya ketika saya menulis proposal buat research grant, itu juga ada beberapa mentor yang di-assign untuk terus mengkaji hasil karya tulis saya supaya lebih gampang untuk bagi saya untuk berkembang juga. Dan itu mentoring. Kalau networking itu masalah apapun di dunia ini tidak akan bisa dikerjakan sendiri. Sebagai researcher kita harus bisa bekerja sama dengan orang lain, baik dalam universitas sendiri, negara sendiri, maupun dalam lingkup internasional, dan tidak cuma akademik saja, tetapi juga bergabung bekerja sama dengan industri. Contohnya di bidang saya ini aircraft design, kita bekerja sama sangat erat dengan pihak-pihak Boeing, Airbus, dan juga sekarang mulai beberapa perusahaan di Cina. Itu kenapa? Karena dari pihak industri itu mereka bisa bercerita kepada kita masalah-masalah apa yang mereka hadapi, masalah-masalah apa yang mereka perlu kontribusi dari pihak akademik, dari pihak pure research untuk membantu mereka. Jadi kerjasama itu perlu, makanya networking itu perlu. Kemudian yang terakhir adalah proaktif. Proaktif itu dari segi researcher kita harus berani memasuki bidang yang baru. Kita harus berani mempertanyakan pertanyaan-pertanyaan, masalah-masalah yang baru. Jangan sampai kita stuck di persoalan yang lama yang sudah saturated after a while gitu. Dan juga proaktif untuk terus menjual research kita ke industri atau ke jurnal international journals, itu sangat penting. Dan juga kalau misalnya researcher itu yang saya pelajari selama ini, salah satu kuncinya itu adalah untuk tebal muka. Kita nggak boleh malu kalau kita nggak tahu gitu. Dan itu sama aja, kembali ke proaktif. Kalau misalnya nggak tahu, ngaku aja nggak tahu, dan itu bagaimana cara kita bisa belajar secepat mungkin. Jadi sepertinya itu saja sumbangan dari saya, semoga bermanfaat. Dan itu foto kampus tempat kerja saya. Bagus ya? Oke, makasih.